Welcome back, math friends. We're going to be talking about simplifying trigonometric expressions using identities today. We will also use these when we start solving equations, but for now, we're just going to work with some expressions. As a reminder, when you are working with these trigonometric functions, we have the 6 functions that we typically use: sine, cosine, and tangent, and then their reciprocals. The reciprocal of sine is cosecant, the reciprocal of cosine is secant, and the reciprocal of tangent is cotangent. And when we are in the unit circle, the radius is 1. And so that would be just sine is y, cosine is x, tangent is still y over x, but then cosecant would be 1 over y, secant would be 1 over x, and cotangent would still be x over y. So for the unit circle, we have y, x, 1 over y, and 1 over x. And that's going to help us with our identities. If I was to rewrite and solve for y and x in terms of sine and cosine with theta, let's say I'm talking about the unit circle. That would mean that y would just be the sine of theta. But if I wasn't talking about the unit circle, y would be equal to r sine theta. That would be multiplying both sides by r. I'm going to use those to help me with the identities, okay? So let's say that we're using a unit circle here, then I'm going to have y is equal to sine of theta and x is equal to cosine of theta. When I have x squared and y squared equals 1 for the Pythagorean theorem, let's just refresh really quickly in this unit circle, very basic sketch. We're talking about some function here where we have x and y and the radius is 1, and that's a right angle form. So x squared plus y squared does equal 1 squared. Using the fact that x is cosine theta, then I'm going to have the cosine of theta squared plus the sine of theta squared is going to be equal to 1 squared. Whenever we square a trigonometric function, you actually take the square and put it in between the theta and cosine. That's going to be the cosine squared of theta plus the sine squared of theta is going to be equal to 1. That's our first trigonometric identity. If you divide by cosine squared theta and sine squared theta, we get 2 new identities. Simplifying, remembering our trigonometric functions that we've listed, cosine divided by cosine squared is 1. Sine over cosine is tangent, and that's tangent squared. So 1 plus tangent squared of theta, and 1 over cosine is secant, becomes secant squared of theta. To the other side, cosine divided by sine is cotangent. That's going to be cotangent squared of theta, plus sine squared divided by sine squared is 1 of theta. And then 1 over sine is cosecant, so that's going to be cosecant squared of theta. And those are 2 more identities that we have. Our trigonometric functions are either even or odd depending on their symmetry. If you looked at our trig graphing video, you'll notice that cosine and its reciprocal are the 2 even functions for trig, and then the other 4 are odd. So we've got sine, tangent, cotangent, and cosecant are all odd. And what that means is if you substitute in a negative x value, that gives a negative function because it's symmetric about the origin. And that helps you when you're trying to simplify your expressions. You can use the fact that functions are even or odd. An even function is symmetric about the y-axis, and what that means is if you substitute in a negative variable, you get out the actual function itself back. Now, if I was to take a right triangle and label it using cosine and sine and 1 as if in the unit circle, and then draw out triangles from that to create a square, like we have here. This is, let's imagine that we're in the unit circle and the radius is 1, cosine is our x value, sine is our y value. and then we were to draw these angles, I can use that to create two new formulas for sine of a plus b and cosine of a plus b and what that would be. So you can derive these, but these next formulas where you're doing the sum and difference come from this idea here, and there are proofs of that online. We're going to be talking about cosine and sine, and then they're going to use some version of sine and cosine together, or sine and cosine separated by an addition sign. So these addition formulas, the sine of a plus b is equal to the sine of a cosine of b plus cosine of a sine of b. And then the subtraction is the same thing with the minus sign. And you'll need to notice that the way in which the sign, the symbol of plus minus is written, follows with plus minus. Looking at sine a plus b, you've got sine, cosine, cosine, sine. Sine of a, cosine b, cosine of a, sine of b. Cosine does cosine, cosine, sine, sine, and the symbol is different. So if you're adding in this sum formula, you're actually subtracting those. So you've got plus, minus, and minus plus. What that means is if you have the cosine of a plus b, you're doing the cosine of a, cosine of b, minus sine of a, sine of b. And if you switched it to cosine of a minus b, it swaps. We can then substitute in to this formula for theta and get double angle formulas and half angle formulas. The double angle formula means if you have 2 theta, that becomes cosine of 2 theta. You'll get cosine squared of theta minus sine of squared of theta. And then sine of 2 theta is 2 sine theta cosine theta. The half angle formulas are cosine squared of theta is equal to 1 plus cosine of 2 theta over 2, and sine squared is 1 minus cosine 2 theta over 2. Notice both of these half angle formulas involve cosine of 2 theta, but one is cosine squared and one is sine squared. Depending on your teacher, you might be able to have a sheet of trigonometric identities, or you might have to memorize these. It's dependent on who is your instructor. Let's get into some examples of simplifying using these identities now. First, we're going to simplify expressions, and then we're going to prove a few identities. We're going to simplify this sine theta, secant theta into a single expression. We're going to start off kind of basic. When I am solving trigonometric identities, what I'm thinking of is typically I'm going to use the Pythagorean identity, even and odd functions, and rewriting the trig function in some form. If that's cosecant, maybe I'm going to write it in terms of sine. If it's secant, maybe I'm going to write it in terms of cosine. Tangent, I'm going to write it in terms of sine and cosine. Same thing with cotangent, I'm going to write it in terms of cosine and sine. Sine theta by itself doesn't do anything other than be sine theta. If you're squared, that's a little bit different. So right now I can't do anything with the sine theta, but I can look at the secant theta and rewrite it in terms of something else. I know that secant theta is 1 over cosine of theta. And now I'm starting to see something. I can multiply these two and write that as sine theta over cosine theta. And I know that sine over cosine is tangent. That's going to simplify to tangent of theta. Moving on to the next example. Feel free to pause the video and try and work these out and come back and see how I approach them. Cosine squared of y, just another variable, over 1 plus sine of y. Can't really do anything with 1 plus sine of y, but cosine squared I know is involved in a trigonometric identity. The trigonometric identity that involves cosine squared is that Pythagorean identity of sine squared plus cosine squared equals 1. So sine squared of y plus the cosine squared of y is equal to 1. In the numerator, I have cosine squared. That means I want to go ahead and get cosine squared by itself in this identity by subtracting sine squared y, which means you can manipulate your Pythagorean identities. And I then have that the cosine squared of y is equal to 1 minus sine squared of y. I'm going to go ahead and substitute that into the numerator instead of cosine squared y. Now I've got something that looks kind of like the same, but it's different. I can't do anything with the denominator. That's not squared, that's just a sign. But I do know that 1 is a perfect square and sine squared is a perfect square. Sine times sine is sine squared. 1 times 1 is 1. And there's a minus sign in between the two of those. That is the sum and difference. I can factor that. I can factor that to be 1 plus sine of y times 1 minus sine of y. And write that over the denominator of 1 plus sine of y. And now I see that I have something that's common to the numerator and the denominator that I can divide out. That leaves me with 1 minus sine of y. And again, sine of y does not get any simpler. I can't turn that into something else. It's not squared. My then result is 1 minus sine of y. Secant squared of x and tangent squared of x, I have 1. Well, I do have some Pythagorean identities that involve secant squared and tangent squared. I know that secant squared of x is equal to 1 plus tangent squared of x. I'm going to substitute that in to my equation here. Instead of secant squared of x, I'm going to write 1 plus tangent squared. I then have 1 minus 1 plus tangent squared of x minus tangent squared of x. I can then say tangent squared minus tangent squared is 0. And then I have 1 minus 1, which is also 0. This expression actually simplifies to 0. Let's then verify a few identities. When you are verifying identities, it is best to pick one side to manipulate and try to match the other side. Looking at this, I don't want to take cotangent and try and complicate it to the left. I want to take the left-hand side of the equal sign and simplify it to the right-hand side. I'm going to leave cotangent alone, and I'm just going to work with the left-hand side of the equation. Cosine cannot be rewritten. I'm going to leave that, but I can rewrite secant in terms of cosine, and I can rewrite tangent in terms of sine and cosine. That gives me cosine of x times 1 over cosine of x divided by sine of x over cosine of x. In the numerator, cosine times 1 over cosine, that actually I can divide out that cosine and that reduces to 1. That means I have 1 divided by sine of x over cosine of x. When I divide fractions, I multiply by the reciprocal. I'm then going to take 1 times cosine of x over sine of x. Cosine of x over sine of x is the cotangent of x, which is what I was looking for. So that matches. Identity verified. Moving on to this last example, I have tangent of y plus cotangent of y times sine y cosine y. I can't do anything with the sine times the cosine right now. Those are as simplified as possible, but I can rewrite tangent and cotangent in terms of sine and cosine. Tangent of y is sine of y over cosine of y. Cotangent is cosine of y over sine of y times sine y cosine y equals 1. I'm going to find a common denominator. I'm going to multiply both of these to get the denominator to be cosine y sine y. Actually, I'm going to rewrite it sine y cosine y. That means I need to multiply the first fraction by sine y over sine y and the second fraction by cosine y over cosine y. Sine y times sine y is sine y squared, which I'm going to write as sine squared y. And then I'm going to write sine y cosine y plus cosine y times cosine y is cosine y squared, which I'm going to write as cosine squared y over sine y cosine y. Hopefully you can see where we're going with this. The commutative property multiplication says the order that we multiply doesn't matter, so I can actually switch it to be sine y, cosine y, or cosine y, sine y. Writing that over the same denominator, sine y, cosine y in the denominator, sine y, cosine y in the numerator actually cancel out. I can divide that out. And that leaves me with sine squared y plus cosine squared y equals 1. And sine squared y plus cosine squared y is 1. Do the Pythagorean theorem identities. So that does match. And looking at the way that I approached the first problem versus the second problem, in the first problem, I didn't really carry through the equals cotangent on the right-hand side of the equal sign. It's probably better practice to do it this way, where it's a little bit more easy to follow through, where you're just continuing to simplify through with that equation. Thanks for watching. I hope this was helpful.